session. And okay, so quickly, what is our workshop is talking about? It's a 3-day workshop. We started yesterday. The title of our workshop is Introduction to Seismic Method. First day, we talked about the acquisition. Today, we are going to talk about processing. And tomorrow, inshallah, we are going to talk about interpretation. This workshop is a summary or an introduction to a full course, which should be running in maybe in July. The full course is targeting geoscience students related and or fresh graduates, and maybe a 1 to 2 year experience in oil and gas. The objective of the full course is to give a generic knowledge about geophysics and its role in oil and gas exploration, especially seismic method. Know what is the different type of seismic acquisition in detail. Basic to intermediate knowledge about seismic processing techniques and interpretation as well. Learn about AVO and AVN theory and practice, and some other types of interpretation. And finally, learn how to integrate between these different tools. So our workshop, we talked yesterday why seismic method is preferable method in oil and gas exploration, and how is the seismic stack or seismic image is built. And we talked about different type of seismic acquisition, and we talked about the OBN, ocean bottom node, which is the most recent technique in acquisition. So let me go through yesterday's slides. We divided the geophysical methods into active and passive. The difference between the passive method and active method, that the passive method detect variation or physical property within the natural field associated within the Earth, such as gravitational, magnetic, and some electrical, radioactive, and geothermal methods, where the gravity method depend on the variation of the gravity or the density, and for example, the magnetic method depend on measuring the variation in the magnetic field, for example. And the active method is like the seismic method, which is artificially generated signal transmitted from a source into the ground and then modifies the received signals. We did a quick comparison between gravity, magnetic, and seismic, and what is the advantage of seismic method and why it is preferred in the oil and gas, and some of the application of the seismic method. And we went through quickly some definitions like wave, wavefront, and wave parameter, peak and trough, amplitude, period, and wavelength. And here we talked about the reflection concept or the reflection coefficient, and why do we have peak or trough after we have the trace, and how the stack is built. And we showed a video and explained what is the fold and how it is produced. Then we went to the comparison, quick comparison between the 2D and 3D layout, and what is the advantage of 3D upon 2D, and when is the 2D seismic might be useful. Then we went through different type of acquisition quickly. The marine, land, the marine is the offshore, marine is onshore, the land. Transition, OBC, 4D, and we ended with the OPN layout. OPN stands for ocean bottom node. Also, we showed a quick video, what is the benefit and advantages of the OBN. And we ended up with survey design. It's a little bit advanced point, but I thought it might be useful for you to know or to hear about it. Now we will start for our second day for seismic processing. Okay, the story is, as you know, as you studied in college or in school, we start with the seismic acquisition, which is acquiring data in the field. Then this data is sent to the processing center, where it undergoes the processing. After this, the processing center gives this data to the exploration companies to do their analysis on it. So today, we'll talk about the role of seismic processing, and we'll explain a generic workflow, and we'll talk about the migration theory. What is the difference between PSTM and PSDM? PSTM is the time migration, okay? Pre-stack time migration and pre-stack depth migration. And we will give a brief about the velocity model building as well. The role of seismic processing to increase signal to noise ratio, which results in better image, which is the filtering and enhancement of the image. Processing is mandatory period to interpretation. Through processing, it is possible to detect the velocities for different fluids. So after we do the processing, or one of the output of the processing is a velocity field, which in turn reflects the velocity of the fluids. This is a simple, generic processing flow. First, the processing center receives the data in SIG-D or SIG-Y format. SIG-Y or SIG-D is a international format, or it's a common format that's used by all the companies to read and write the data, or to input and output the data. Okay. What is actually happened that we receive as a processing center, if we considered ourselves as a processing center, we receive the SIG-Y data from the field and transform it or reformat it to internal format, to our own internal format. We are a processing company. We have our own format. So we transform or reformat the SIG-Y data to our internal format. We do our processing sequence. And when we finish, by the end, we transform again the data from our internal format to SIG-Y output format. Okay, so it can be commonly used by anyone. The sequence first start with trace editing. Trace editing, it's a process, but in general, it means that you get rid of any unwanted or bad traces resulted due to some errors in the acquisition. So as simple as the word is, trace edit, you remove whatever unwanted trace that will cause problem further. Then we have a second step called geometry update, amplitude recovery, noise attenuation, deconvolution. Then we go to multiple attenuation and residual noise, velocity analysis, regularization and interpolation, followed by migration preparation, then migration velocity. We do the migration, which is the main target or the main step of our work, post-stack sequence, which comes after the migration. Okay, let me go through the sequence again. This is a generic sequence. The processing, let me tell you something, the processing flow or any processing sequence in any project, it is not fixed. I mean, this steps is not fixed, and you might have much more steps. But here, I'm talking about the mandatory steps. So, for example, there is no processing project can run without noise attenuation or without multiple attenuation, and of course, without migration. This will never happen. You will always have these steps in any processing project. Sometimes you might need to add other steps or other process. Okay, so this is the mandatory or generic flow. Okay, let me go through it again. You get the data from the field. Okay, you do the navigation merge. I will explain what is the navigation merge. Trace edit, geometry update, amplitude recovery, noise attenuation, deconvolution, multiple attenuation, residual noise attenuation if needed, velocity analysis, regularization and interpolation, migration preparation, then migration velocity, then finally migration ending up with post-stack sequence. Okay, let's go first to seg-y, seg-d, which is called the reformat. Data is received from field in seg-d or seg-y format. Seg-y is a common format used worldwide. Processing center changes data from seg-d or seg-y to its internal format. Reformatting process also includes seismic navigation merge. Some more information in the format step. Data is received as tapes 3590 or 3592. That's I missed typo. It's 3 from field. Recent data acquisition mostly are navigated merged. Seg-y tapes are read in the driver of the processing center. Seg-y is transformed to the internal format and headers of the processing center. Seg-y QC is done by building different map of the data to be compared with the navigation data. Seg-y QC is done to make sure that the tape is fully read with no missing data. After finalizing the processing, the data is transformed back again from the internal format of the processing center to Seg-y and written on tapes or disks. Episodic and trace header to be correctly defined in Seg-y. I will explain what is the episodic and trace header. Seg-y QC in this case is done by reading the tapes after writing it to make sure that all the data is on the tapes. The QC is done through mapping X and Y amplitude, fold, and some other attribute before and after reformatting. Okay. The episodic and trace header are headers that carry some informations explaining the seismic, okay? Like the sample interval, the trace length, shoot point interval, some of this information. For the navigation merge, what is the meaning of navigation merge? We mentioned it here. Okay, recent data acquisition is navigation merge. The navigation merge, we have a navigation data. While you are in the field, in the acquisition, for example, you have shot and receiver, as we showed yesterday. Every shot and receiver has its own X and Y. That's one of the navigation data. The coordinate is part of the navigation data. The elevation of the source and receiver is well considered as a navigation data. This navigation data is recorded in the field in files, navigation files, okay? What is the uses of this navigation data? The coordinate or the X and Y's makes the location of shot and receiver fixed. You have a reference, okay? So you need your seismic or seismic trace to be related to the field or to the reality. So what is the reference or what is the relation? It is the X and Y's and elevation, or between brackets the navigation data. So the navigation data need to be defined on the seismic traces. So the seismic section reflects the reality. That's what the meaning of navigation merge. What really happened? That you take this navigation files or navigation data and insert it or merge it with the seismic traces. Now I will go to the trace edit. As I said in the introduction or the beginning, it is the removing of bad shot from record if exist. The bad shots or bad traces happens due to dislocation in source or any error occur during the shooting process. Bad shot is mentioned in OBS, observer logs. Simply, it is deselected from the data. What is the observer log? The observer log simply it's the report that contains the details about the shooting process. For example, shoot number 100, it has a bad trace or a certain bad trace. This is mentioned in this observer log. So the observer log is produced daily, day by day, okay? And it mentioned all the details and the timing of the shooting process. So in the observer log, you will find all the bad traces numbers. For example, you have here one shot. This is a shot gather, okay? And here is the trace with the high amplitude. It is considered as a bad trace. So it is deselected from the record, okay, to be like this output. This is the input, this is the output, and this is the difference. What happened here? That this trace is deselected. I will explain how it is removed as we go further. I will tell you how this trace is removed. Then we go to the noise attenuation. What is the definition of the noise first? Okay, all what we have in the seismic section, all of it is called signals or traces. So all of these are signals or traces. The signal carry desired information. The noise contain unwanted information. The noise is unwanted signals. So the seismic section or seismic data, all of it considered to be signals. The unwanted signal or the bad signals is defined as noise. Okay. Let's classify the noise, the noise types. We have random noise and we have coherent noise. Random noise, from its name, it doesn't have pattern or a trend, while coherent noise is predictable or noise which has trend. Okay, it's as simple as that. Random noise, it doesn't has a trend or it is not predicted, while coherent noise has a trend and it is repeated and predicted. This section or this shot shows different kind of noise. Okay. This is facility noise, vehicle noise, air blast. Okay, that's one of the most important slides that we are going to talk about today, the frequency filter. Okay. Let me tell you something in the processing in general. When you need to get rid of bad signals or noise, you target or you aim one of the properties of the wave. Yesterday, we talked about some properties of the wave, such as frequency, wavelength, and velocity is part of it as well, and amplitude. Okay. So when you do cleaning or removing noise, you target one or two of these properties. Okay. For example, here, I call this bad trace high amplitude bad trace. So here I target high amplitude. For example, okay, here for this kind of noise, we have a high frequency trace, high frequency wave. So here we target traces with high frequency to remove. Okay, so generally in noise attenuation or in processing, we are targeting parameters related to the wave, such as frequency, velocity, amplitude, or we may target more than one parameter in the same time. Let me go directly to this example. What I'm going to explain to you now, it is what is really happening in the processing center, okay? Here, I have a bad trace or noise or unwanted signals that I want to remove, okay? This high amplitude. What is the analysis done for this? So I get like a window, I design a window, this window, I design a window with a certain number of traces, let's say maybe 21 traces, for example, okay? And here I have a high amplitude trace. What's happening here? Within this window, inside the 21 trace, we calculate something called the mean amplitude or the K constant, okay? What is the K representing? It is representing the median. Let's say, for example, the average amplitude. It's not the average amplitude, but it is the median amplitude. But if we added all the amplitude and we get the median, we will have K. The K is the threshold or the reference for the median value. After this, the process or the algorithm or the job, what it's doing, it compares the amplitude of each trace with the K, with our median. So we have 20 traces. So for the first trace amplitude value, within this window, it is compared with the median. If it is the same value, it will leave it. If it is higher, with a certain limit, it will be removed. For example, we calculated the median within this window to be, for example, 5. Okay, value 5. Then we are comparing the amplitude trace by trace, until we get this high amplitude. We found it. It is 3 times larger or greater than the K. It equals 15, for example. If the amplitude here is equal 15, it will be rejected or removed. Okay, that's what's happening here. He found a high amplitude value higher than the median calculated by 3 times. That's our condition. So it is removed. This is the input, this is the output, and this is the difference. We usually do difference to make sure that we didn't remove anything else but noise. We didn't remove any signals. We're only removing bad traces. Okay? Let me go through it again. We have a window. We have a certain window. We have a high amplitude or bad trace, okay, within certain range of frequency. We calculate the median, not us, the computer or the program computes an amplitude median, okay, median for the amplitude values for all the traces inside the window, okay. After this, a comparison process is done trace by trace. Within the window, trace by trace amplitude is compared to the median value. If the program found that the amplitude of the trace exceeds the median amplitude value by 3 times, for example, it is removed. Okay? We put this condition. I put the condition 3K. If it is the amplitude of the trace exceeding the median amplitude 3 times, please remove it. And that's what's happening. Okay? So here we targeted the amplitude value to do the noise attenuation. Okay. One more point is the velocity analysis. Okay. The velocity analysis or the normal move out. What is the normal move out or the velocity analysis? Okay. Let me explain on this figure. This is the shot, okay? And we have receivers along here, as we said yesterday. This is the time axis. Okay. So we shot here and reflect and receive, okay? again and again and again. This is the traces. What do you think will happen, or what do you expect as the distance increase or the offset increase? This x is called offset. As the distance increase, just imagine that you are walking from, we have 3 points, okay? Now here, we have S, we have x1, x2, x3. The time that you will take from S to x1 is shorter than that you will take from S to x2, is shorter than the time you will take from S to x3. That's normal, okay? So as the offset increase or the distance increase, the travel time as well increase, okay? This is the axis of the time. So reflecting on a horizontal layer, flat layer, will result in this hyperbolic shape, because as the distance increase, the time, travel time recorded also increase, okay? So for a flat event or a flat reflector, you will have this hyperbolic shape. The velocity correction, okay, what is the relation between the distance and the time? Normally is the velocity, okay? So to make correction or to make this hyperbolic shape flat, because we already reflected on a flat horizon, we need to compensate this difference in time. To make it flat again, we need to compensate this travel time differences, which is called the normal move out process. Okay, this is a move out event, and this is after correction, after we compensate the travel time. If it went upward, that means it is overcorrected. That means that you have fast velocity. Okay, let me explain it again. This is our start point, and we have different receivers. If you went so fast, the travel time will be short. If you went slow, the travel time will increase. Okay? This is the example for velocity analysis, or that's what really happened in the processing centers. Okay, here you have uncorrected gathers. You have here uncorrected gathers. What happens here? That you correct the move out or the delta t. How this is happened? By changing the velocity values. This scale is for the velocity, and this is for the time. This is called semblance display. You choose certain velocity. You have different velocity values. You try some velocity or different velocity. It will turn to be flat. When the equation is applied with a new velocity, the undercorrected gather is corrected to be flat. The flat event means that you have zero move out. You have no error. Okay. Why we are doing this? Let me tell you why we are doing this. As we said yesterday, this is a gather, CMB gather. In order to form the stack, in order to have a full stack, we stack or we sum different CMB gathers. So the stack actually or initially is a group of summed gather. To have, so you can see the horizon here. For example, you are summing many gathers from this. Okay, you have gather 1, 2, 3, 4, 5. So if you put them beside each other and you do a summation, it will give you the full stack. Okay, so the one gather is the unit of the stack. So imagine if you try to sum group of gathers like this with this, it is undercorrected. You will never have event defined. Okay, let me flip between these two. This is stack before velocity analysis, and this is after. Before, after. Before and after. Before and after. Okay. As you can see here, the image here is not clear, but now after velocity, it's more clear. Why this happened? Because you can say that after move out, you have a constructive interference for the event. But if you try to sum the gathers like this, you will have this dimmed output. So here, the gather is not corrected. So the interference or the summation is not matched or it's not good. The traces are not aligned well. But here, after the trace alignment, the summation or the stacking give a better resolution. This is the main target of the velocity analysis. To correct, first to compensate the move out phenomena. The move out phenomena happened due to increasing of the distance or the offset will result in increasing in travel time. After we compensate the move out, okay, after we compensate the move out to make it flat, we do the stack or the summation of CMB gathers. Again, this is before, after velocity, and this is after. Before, after, before, after. So let me show, for example, here again, this part, before and after. So as the gathers are aligned and correctly summed, we got better resolution. I will go directly to the practical part. Okay. Let me first define what is the multiple. We have primary energy. The primary energy is the one coming normal, as we know. This is the black one. The black one is primary. We shoot, reflect, and receive. That's a primary reflection. We have something called multiple. From its name, it's multiple reflection, which means that it did several reflection before being recorded. This is considered as a noise or error or unwanted signal, okay? Because it is not real. You have a reflector or a horizon. What you need to record is the one-way time and another one-way times, two-way time, okay? That's your real reflection. But here, it is double the two-way time. It is double the two-way time. We don't need this. It will cause error. Let me go directly to the example. Before going to the example, what do you think the travel time value will be? It is double, yes? Okay. What also it means that we have a higher or a higher travel time. That means that you covered a longer distance, yes? We just said it in the normal move out. We said that as we have the distance increase, the travel time as well increase. So we have the hyperbolic shape. So imagine now that you have more travel time. That means that you covered more distance. That means that you will have more hyperbolic shape. Okay? So simply, the multiple recognized on the gathers with a very hyperbolic shape because it took double the time of the original signal. Okay? So what we need to do is to remove these hyperbolic shapes. This is multiples. Okay, how this can be achieved? First of all, before removing this, you need to make sure that your data is undergoing a move out correction. Let me go back again to this example. Imagine that you have multiples here on this data. For un-NMO'd or a non-moved out corrected gathers, can you discriminate between multiples and primaries? You will never do. You cannot. You can't discriminate here between multiples or differentiate between multiples and signal, because the gathers is not corrected. It's not NMO corrected. Okay. So you need to make a move out correction to be able to discriminate between multiples and primary. So we do the move out first. After you do the move out, whatever has the hyperbolic shape, it will be considered as multiples. Now you can target it and remove it. I will show you before and after. That's before multiple attenuation. This is after. You can see the difference clearly. Yeah? Before and after, before and after, before and after. Before and after, before and after. Okay, the migration and the migration is our main target from the processing. Okay, what is the definition of the migration? A process which attempts to correct the distortion of geological structure inherent in the seismic section. Migration redistributes energy in the seismic section to get a better image consistent to true geological structure. I would like to go to this example. Okay. Let's start with the syncline first. Here, okay. We all know the syncline as a geological form, okay. In reality, synclines looks like this. In reality, synclines in geology looks like this. In seismic, before we do migration, it will be like this bow tie. How this shape is resulted from? From where did we get this shape? I will go back to this nice display. Okay. Here is the geological part, and this is the seismic or the subsurface part. This is the surface, and this is the subsurface. Okay. I will go now trace by trace. Okay. This one resulted in this trace. B resulted in this trace. B again resulted in the second one here. After we finish the set of reflections and each trace is put in its place, it will result in this shape. Okay, like a cross. If you match it this as a horizon and match it this, okay, it will give you this shape, the bow tie shape. Okay. So what is the migration is doing is to get the traces to the original geological form. How this is done? By moving these events upward and moving these events upward. This is the migration. What does the migration do? The migration do three things. I prefer to explain this. I prefer to explain this before defining the migration to make it easier for you. I will go a little steps. Yeah, okay. Migration, rearrange seismic data so that reflection event may be displayed at their true position in both space and time. The migration moves the data laterally in up dip direction, upward in time. Okay, I will go back to this example. So imagine that we moved this part, this event upward, and we moved this part upward. It will result in the original syncline shape. That's what the migration is doing. Okay, it change the position and location of traces to go back to the original geological position. Same example for the anticline. Okay, this is the stack before migration, and this is after. You can see here that there is a collapse between the flank okay, and the data from here. Okay, we have interference. So if we imagine for this part that we move this upward, we will move this upward, okay? It will be like this, and it will be consistent with the flank. This is the correct geological form. So what migration is doing is correcting the position of the traces in space and time. Okay. The details, of course, it's more advanced and more complicated, but this is the simplest way I can tell you the migration is doing. This is an example for salt dome definition. Okay, this is before migration. You can imagine that there is a salt dome, but you cannot see the boundaries. Okay, after the migration, you can see the salt dome borders. For the migration, we have two different types. We have something called PSTM and PSDM. PSTM refers to pre-stack time migration, and PSDM refers to pre-stack depth migration. The advantage of the depth migration, the time migration, it's correct vertical positioning, correct lateral positioning, improve resolution, allow velocity and depth estimation. Well, in reality, PSTM do this as well, do this job, okay? But PSDM, due to the algorithm or the way it is working, it make more correction or better correction vertically and laterally. Let me tell you why this also happened. Simply, from this figure, the PSTM and PSDM do something called array tracing. Simply, in order not to confuse you, let me explain the difference between them. This PSTM tracing is going like this, from layer to layer, 1D, or in one direction through the interval. For the same interval, the PSDM, it doesn't go in a 1D method or a 1D trend. It goes, rather than this, goes in a 3D. You can see here for this interval, it is not going directly like this in one direction. It goes in different direction. So you can see the difference between the ray tracing. So the PSDM ray tracing or correction process, okay, or the migration process is different. It takes into consideration more lateral and vertical variation than the time. That's as simple as that. So the PSTM methodology or algorithm is working in 1D through the interval, okay? Only one direction through the interval. But the PSDM algorithm works in a 3D mode. It goes through different direction in the same interval. So it get or capture more details. So that's why the depth is always better than time migration. That's, for example, the difference between PSTM and PSDM, migration in time and migration in depth. As you can see here in depth migration, the dome is better defined than the time. That's all for today for the processing part. Usually the processing is not as easy, and it cannot be explained all of it in 1 hour. However,